In this video, I'm going to be talking about another approach for event extraction, and we are using the paradigm of Fewshot learning, and the technique that we use is based on prompt guided identification and localization. We do it for event detection. So I'm going to be focusing on this paper in 2022 from Carnegie Mellon. P4E is the name of the model. So we propose P4E, an identify and localize event detection framework that integrates the best of Fewshot prompting and structured prediction. Our framework decomposes event detection into an identification task and localization task. For the identification task, which we've formulated as a multi-label classification, we leverage close-based prompting to align our objective with the pre-training task of language models, allowing our model to quickly adapt to new event types. We then employ an event type agnostic sequence labeling model to localize the event trigger condition on the identification output. This heterogeneous model allows P4E to quickly learn new event types without sacrificing the ability to make structured predictions. We first recognize the event types in the given context, the identification stage, using multi-label classification. And then find the trigger location. That step is called localization step, through structured prediction. We call it structured prediction because this sequence labeling is just one of the approaches that we use. For example, if you combine CRF, LSTM, and those methods, those are just one of approaches for structured prediction. So we propose to decompose the event detection into stages of identification and localization. By decoupling the type semantics from sequence labeling task, we bring the benefits of clause-based prompt learning to event detection and enable maximal parameter sharing across the event types, greatly improving the data efficiency of our model. And we extend the clause-based prompt learning paradigm to multi-label event type classification. This enables us to leverage the language modeling ability of pre-trained language models for the event identification task and adapt quickly to new event types. This method can be applied to other multi-label classification tasks. So given a collection of contexts and predefined event ontology, this is our event ontology, which is a set of target event types. Event detection aims to find all event mentions in the collection that fall into that given ontology. An event mention is characterized by a trigger span. It has a start and end of that span, and even an event type. Here we follow previous work and consider each sentence as the context of the event mentioned. We divide event detection into two stages, identification and localization. In the identification stage, we find a set of event types that have been mentioned. In the localization stage, we take a pair of context and event type as input and find a set of spans that correspond to triggers for that event types. Note that both stages can produce a variable number of outputs for each input, and each sentence can contain multiple event types, and each event type can have multiple triggers. The event identification model follows the idea of this article in 2021, which uses masked language models. So the prompt is a natural language sentence with a mask token. And so the relationship between the class labels and the predicted tokens for mask is defined by a verbalizer. The verbalizer function, F is the verbalizer function, because it relates your class labels with the predicted tokens for the mask. So during prediction, we use the logic that the mask language model assigns to the verbalizer for label L as the proxy for predicting L. In the classification task, the probability for label L can then be computed like this. For event detection, since each sentence can potentially mention multiple event types, we extend this approach to handle multi-label classification. Through the mask language model, we score all tokens in a vocabulary under likelihood to fill in the blank. After excluding tokens that do not map back to any event type of interest, we obtain a ranking among all event types. So we assign V null to null type, and we use an adaptive threshold. In the inference stage, we predict all event types that score higher than the null type to be positive. So during training, for each sentence, we compute the loss for, this is the loss of positive event types and negative event types separately. This is the loss for negative event types. And T here is just this T, or cardinality of T, is the set of positive event types for the sentence. And T bar is a set of remaining, which is the negative event types. Note that in computing the positive loss term, we only compare the probability of positive labels to the null label. And then we sum the positive and negative loss. But verbalizer selection is important. We first collect a candidate verbalizer set from the training set examples trigger words. Then we use a frozen language model to score each candidate by plugging it in the class prompt of our identification model. The selection for each event type is done separately. We compute the score of a candidate verbalizer for event type with class label L sub t using the reciprocal rank scoring function, where R sub I is the predicted ranking of the candidate verbalizer from the frozen language model. Trigger localization is the task of finding a trigger offset given a context and an event type. Our localization model is a linear chain CRF tagger with only 3 tags: begin, internal, and outside, something that is not inside. And in this way, the model parameters are not tied to any event type and can be easily used to transfer. So the probability of tag sequence is this. And I have a playlist for CRF if you're not familiar with which I talk about transition probabilities or emission probabilities. So we parameterize the emission scores. This is the emission scores. And so we parameterize it, and we have some attention here. And then we do joint training. This is an example for the localization model. You see the context, you see the field prompt, the text describes a higher event. And then you see the tagged context. So we have different data set, few event, because we are using Fewshot learning, Maven. We had 45 types. but it has some limitations. Our model requires human design prompt and verbalizer, and those are limitations.